Here's a quote from your book. What has always distinguished calculus from algebra is its ability to deal with variables that change over time. So you have probably seen the formula for the volume of a sphere before. Maybe you found a way to derive it in geometry class. Maybe later when you were in Algebra 2, you practiced cube roots and you solved this formula for R. So you've manipulated this formula, you've used this formula to find volume, but you have never used this formula to solve a problem about a sphere whose volume was in the middle, like in the process of changing. So I think it's a wow, because that's a big deal. Imagine somebody blowing up a balloon or a soap bubble. The volume is changing, and we might want to know how fast the volume is changing. And we might be interested to find out that the volume isn't always changing at the same rate. The rate at which the volume changes is changing. So we can answer questions about this, how the volume of this bubble is changing, using the techniques of chapter 4.6. What you really need to know is that a related rates problem is really just a big, fancy, implicit differentiation problem. So that means we have to remember everything we knew about implicit differentiation. I'm going to remind you in case you forgot. So if I have this equation, y squared plus x squared equals 17, I don't have y isolated. So when I take the derivative, I'm not using the regular old derivative and chain rule formulas that I'm used to. I have to differentiate both sides with respect to x, and then try to isolate the dy dx expression. So I'm going to take the derivative of both sides with respect to x, but the derivative of y with respect to x, we can't take the derivative of a function of y with respect to x except by using the chain rule. So the derivative with respect to x of y squared in this case is this 2y dy dx. So I can go through that process. I can isolate dy dx and find the slope of this curve at any point. I can find an expression for dy dx. I could just as easily have used different variables. There's nothing special about x and y necessarily. So you can see I've done the same problem here. If I wanted to find dp dt, I would just differentiate both sides of this equation with respect to t, and I can isolate the dp dt expression. So think back to the sphere, our big soap bubble that we're blowing up. The volume is increasing as time goes by. That means the rate at which the volume is changing, the rate at which the volume is increasing, is changing with respect to time. So to describe that change, we would call that dv dt, the rate of change of the volume with respect to time. So if you go back to your regular old happy formula for the volume of a sphere, if I asked you to find v prime, you would say, oh, okay, well, v is a function of r, so I'm going to differentiate with respect to the variable that's there, and you can find v prime. I'm going to ask you instead to take the derivative of v with respect to time. Time is not a variable in this formula, so I'm going to have to use the chain rule. I'm going to take the derivative of v with respect to r, the variable that is there, and then multiply by dr dt. So I'm going to think about that for a second. When I take the derivative of v with respect to r, I'm going to take the 3 to the front. The 3 is going to multiply the 4/3 that's there. The pi is just a constant multiplier, so that stays. And my new exponent on r is 1 less. That's how I get this r squared. And this dr dt comes from the chain rule. I'm differentiating with respect to time, a function that only has r's in it. So notice this, because if I told you, like I did here, that dv dt is the rate of change of the volume with respect to time, well, what do you think dr dt is? Dr dt is the rate of change of the radius with respect to time. So that means the radius of this sphere is also changing. So that's important to think. So think about somebody started a balloon like here, and they're going to blow it up. The volume is definitely increasing, but look, so is the radius increasing. And that's interesting to note that how fast the volume is increasing is related to, because I can see they're related in this equation, how fast the volume is increasing is related to how fast the radius is increasing. So that's how we get this term related rates for the problems that we're going to be working on. Okay, so you can see here our answer to the first question on your page. I've taken the derivative of v with respect to time. That's 4 pi r squared times dr dt. If we happen to know how fast the radius is changing with respect to time, maybe I know that the radius is increasing, whoops, there we go, increasing at a rate of 0.1 centimeters per second, I can actually find out how fast the volume is changing at that exact moment. So I'm going to take my formula, which is 4 times pi times r squared times dr dt. So here I have 4 times pi instead of r. I've been told at this exact moment r is 10 centimeters. I'm going to plug that in for r. And dr dt at this exact moment is 0.1 centimeters per second. So I'm going to simplify. I get 40 pi centimeters cubed per second. Notice that's centimeter times the centimeter from the numerator divided by second. So centimeters cubed per second. And notice, you should always double check your units in a related rates problem. See, dv dt, that's volume over time. Look, I have units of volume over time.